In order to introduce the concepts about equilibrium of reactions, it may be useful to look at the chemical reactions at the molecular level. So this is why we're gonna click on this link, and there's going to be a simulation, and the first thing we're going to do is to add 10 molecules of both reactants. So the reaction here is A plus BC, that's going to give AB plus C. So a fairly simple reaction, and notice that even though we pumped already only 10 and our total average energy is here, there's already one molecule that has turned into products. So that's the main question here. How can it be if the total energy is below the transition state, right? So you can see here that the total energy is below the transition state up here. How can it be that you can start seeing molecules react? And this may even be, so let's increase the temperature. Now see that the products now went back to reactants. Even if we increase some more, let's make sure we stay below the transition state. Alright, so on average, the energy of the molecules is below the transition state, so on average, they should not be able to reach. So how can it be that some reactants are able to become products? And that's because the energy is not always equally distributed. There may be some reactants that move faster, that have the right energy, that they have the right collision to pass the barrier. So notice that there's been, even though we're still on total average below the transition state energy, some reactants have already become products. So now what happens? Now the next question is, do all reactants become products right away? Let's see if we can increase the temperature so that we are above the transition state. Okay, notice that now we have some, and so the question is, do all reactants become products right away? No, there was a process. The reactants needed to collide with the right orientation and with the right energy. So no, not all of them, because not all of them have the right amount of energy or the right amount of, or the right orientation. However, notice that sometimes some products go back. So this is something that we call dynamic equilibrium. At some point, you will see if we had more, let's add some more. Okay, let's add 20 of each. 20. Okay. It's more than 20, but notice that the situation has reached somewhat an equilibrium, a static case. Does it mean that the reactions stop? No, reactions never stop. So does it stop reacting? No. However, does the proportion, of course, if we had a larger number of molecules, the variability wouldn't change this fast, but you would see that at some point the proportion of reactants and products is the same. That does not mean that the reaction stopped. It just means that the reaction going forward is equal to the reaction going backward, so that the concentrations of reactants and products remain constant. Okay, so I'm going to underline what I just said here. The proportion of reactants and products at some point is constant, but the reaction is dynamic. When you reach this situation, we call this that equilibrium. So the equilibrium situation for a reaction takes a while to reach, and the proportion of reactants and products will be related to how stable reactants and products are. In this case, notice that reactants are more stable, so expect to have always, or typically always, more reactants than products. We can, if you really like this, we can add more reactants and products so that the variability is less remarkable. You will see that these numbers comparatively they change less. Okay, so again, take home message: we reach a situation after some point, provided that it has the right energy, we reach a situation of equilibrium in which the concentration of reactants and products, or the proportion of reactants and products, remains constant, that does not mean that the reaction stops. It just means that the equilibrium is reached when the rate of reactants going into products going forward is equal to the rate of products becoming reactants, the reverse. Okay, when you have this situation, that's what we call equilibrium, and that's very important to keep in mind. Every time we talk about equilibrium, you must have the molecular explanation for what equilibrium is. Equilibrium is essentially dynamic.